All right, so in this video, we're going to just be briefly overviewing the PhET on acids and bases. So it's actually a really helpful PhET to kind of explain what's going on in terms of what we define as an acid and a base. So you're basically going to be drawing out the ions in terms of what's your hydronium versus hydroxide concentration here. Basically, you're going to copy it as the PhET shows you. You're going to copy the equation, color the pH, what is the actual pH, and the strength of conductivity. So we'll kind of jump back and forth of what you guys should at least be able to understand just by playing around with this. I won't go through all of them, but we'll do a few and kind of get you guys going here. So when you open up the PhET, it's going to look something like this. Just make sure it's all reset for us. So when you open it up, just click on Introduction. And then this is what you're going to really be looking at. So let's kind of just take a quick look at what we're going to do first. So first and foremost, let's look at water. Water is nice and easy, and let's hopefully you guys understand what pH is. Now, if you haven't watched the videos yet, you really need to make sure that you understand what pH is in terms of what it's measuring. So realistically, one thing that I think a lot of people get messed up on is pH is going to be equal to actually the concentration of your protons, okay, or hydrogen ion concentration. So I refer to them as protons quite a bit. Just in AP Bio, we talk about protons quite a bit. So one thing that you need to understand is that if you increase the concentration of protons, and those little brackets represent concentration, you're actually going to be lowering the pH, okay? And vice versa. If you have a relatively low concentration of these protons, you're actually going to be increasing the pH. So these two are going to be essentially an inverse relationship. So the more protons you have, the lower the pH, and the less protons you have, the higher the pH. Now, keep in mind, we're really going to be looking at this in terms of water, because a lot of these solutions we're looking at is going to be looking at water as the solvent, okay? So the reason why I wanted to put this up here is because typically, if you have a high concentration of protons in a solution, that proton is going to actually want to combine with water to make this H3O plus, okay? So one thing that we're looking at, another way that we can kind of consider this, if pH is a concentration of your hydrogen ion concentration, we really can just look at this. If you look at the concentration of your hydronium ion concentration, if you increase your H3O plus concentration, it's actually going to decrease the pH, right? And vice versa. So if you have a high concentration of those hydronium ions, it's because there was a lot of protons, okay? Now, a little bit of ahead of ourselves, but for example, if you had hydrochloric acid, that can be the proton that gets donated. So that proton is going to go to water and form that hydronium ion concentration. So I just want you to understand it from both standpoints, that you're going to be looking at hydronium ion concentrations for sure. But really, for anybody taking AP Bio, we also look at it in terms of your proton concentration, but they're the same thing. So let's go back to this. Let's take a look at water. There's a couple of things that we can look around here. So I like to show you the solvent first, just for this one. When you look at the solvent, there's all of this is just water, right? So all of the kind of grayish looking ones is representing water. So the majority of this whole solution is water. Now, if you hadn't watched the videos, you need to make sure you understand that water can actually, it's what's considered amphoteric, which basically means it can act as an acid or a base. Now, all of the water molecules that I have in this beaker, there's a really small percentage that actually forms a hydronium ion, and then there's a small percentage that actually forms these hydroxide ions. So remember that if you measure your hydroxide, the more hydroxide or OH minuses you have, the more basic your solution is going to be, so the higher the pH, okay? So realistically, when you look at this, I have 2 hydronium ions and I have 2 hydroxide ions, and for the most part, this should balance out. So if we looked at the pH, yep, it makes sense that it's going to be 7. So when you go back to the worksheet, when you draw the ions, you would really only have to at least draw in 2 hydroniums and 2 hydroxides, and that would be that. So the equation is this. You would just literally copy this. The 2 waters can dissociate. One can form a hydronium ion and one can form a hydroxide, giving you a pH of 7. So the color of the pH paper, maybe, at least I'm hoping that you guys have done this before. Here's basically going to be looking at the litmus paper test in terms of this. You're going to be looking at, not litmus, I'm sorry, just your pH paper. You're going to correspond the color of this paper to what the pH is going to be. So if we basically had this piece of paper, if we were in a lab and we put it in the solution, dipped it in, it's right at around 7. Okay, so that's how you're going to be reading this. So pH, in terms of what you should be filling out, I would say that this is yellow, matched up with a pH of around 7. And again, I actually told you that. Now, in terms of this one, the conductivity, does it have or produce a charge? And it's kind of tough to see with the white background. But if I put these two in, it is going to actually light up this bulb, okay? So it does have some form of conductivity, okay? Now, water, I think for the most part, you guys are gonna be pretty well understood on that. You know it's gonna be a pH of 7, it's pretty neutral. So let's go ahead and reset this one. And if you look at the graph, I like this graph a lot. If you look at this, it's showing that the arrows can actually go in both directions. We haven't actually talked about equilibrium yet, we will. But this basically means that you're going to basically, when this whole thing is done, when you're actually letting this reaction play out, the majority is going to be remnant, or I should say remaining as this, okay? It wants to essentially be water. So only a really, really small percentage actually form hydronium and hydroxide ions, okay? So that's something that you at least want to make sure you feel okay with. So I'm going to go ahead and move on and actually reset this, and we'll do a strong acid. Now, if you, again, I cannot stress this enough. If you haven't watched the notes from Ms. Toth, I would highly advise that you go through and do that because it's going to be much more detailed than what I'm providing right now. I'm just going through just to kind of revisit what is a strong acid. And remember that a strong acid is going to completely dissociate. So basically what that means is if I had something like hydrochloric acid, right, and I mixed it in with water, that proton right here is going to get donated, or that hydrogen ion is going to donate its water, and then we're going to be left with chlorine with a negative charge plus H3O plus. Okay, so you did form your hydronium ion. Now, when we say it completely dissociates, that's basically being a strong acid. All of the if I did have hydrochloric acid, right? All of the HCl would actually want to donate their protons to water. That means whatever's left is going to just be these chlorine ions. So let me jump back to the FET. I'm going to keep that. So if you take a quick look at the FET on this one, we're going to look at the strong acid. Now, don't let this freak you out. The H with the A is almost like a variable in math, right? So in terms of this, this could be chlorine. This could be any particular acid. Remember, when we write acids, we're going to write the hydrogen in front just to show that it's going to be the proton donor. And then water, in this case, is acting as the base, right? Because it's actually accepting that proton. So if you jump back to this, I could call this, if we were thinking about it in terms of that equation, it would actually still follow with that H. A would essentially be chlorine here. So A would be this right here, okay? So let's kind of take a look at this and make sure that it matches up with that vocab in terms of completely dissociating. And so when you take a look at the FET, first and foremost, let's measure the pH. So we're saying that we have a strong acid in here. So the fact, before I even stick this in, it should make sure that you understand that the pH should be less than 7, because that's what's going to define as an acid. So it's the concentration of the hydrogen ion, like I told you at the beginning. The concentration of your hydrogen ion or proton is going to be the same thing as your proton concentration. So stick it in, yeah, it has a pH of 2, so it's pretty acidic. So you would, in terms of this, write the equation down, which is going to be HA plus water is going to dissociate into your anion, right, your negative charge, and then plus your H3O plus, okay? So in terms of that, that would be your equation. Let's look at the color of the pH paper. So I'm going to change this to the pH paper. It should be somewhere over here, right around 2. It should be red. Yep. So I would, again, record it as a pH of 2 because I had that earlier. Strength of conductivity. Let's see this. Let's find out the conductivity here. Very conductive. Okay, and it has to deal with that chlorine ion, right? In terms of this, there's a lot of charge going on within this solution, so that's pretty ridiculous. So when you compare that back to water, there's a slight little bit of conductivity when you compare that to a strong acid. Man, it's definitely super conductive. So with that being said, let's look at the solvent again. And you didn't have to do this on the worksheet, but I do think it's worth your time. When we talk about that dissociation, like if it's a strong acid, it's going to completely actually react to form this. So this basically means that after I mixed in this hydrochloric acid with water, what's left, I'm not necessarily going to have any more HCl. It's actually going to form all of the H3O plus as it possibly can. I'm not going to have any HCl in terms of that actual reactant. It's going to be left with Cl minus plus H3O plus. Okay, so that's when we say it completely dissociates. That's what we're referring to. Now, if you compare that to, like, let's say a weak acid. Now, if you jump back, actually, I'm getting a little ahead of myself. Let's go back to the molecules. Looking here, I'm going to remove the solvent. I don't see any of the like the H with the A in terms of like if this was HCl. I don't see any once I've mixed it in with water. Okay, I see a lot of the charge from the anion, right? I see a lot of the H3O plus. I don't necessarily see any water left. But if I change that to a weak acid, so it's still an acid, right? If I changed it, the pH is still going to be 4.5. But look at the difference here. I still have some of that H with the whatever variable this would going to be. So if I had something weak like acetic acid, that would be something that you want to be aware of, that it's not necessarily going to completely dissociate. And that's when you look at the graph. I like this one a lot. You're still going to have some that hasn't necessarily reacted with the water itself to form your hydronium ion. So that's what we're going to refer to as essentially a weak acid. Now, before I call this video, you're basically going to be copying this down and then answering these questions. And these ones should be pretty straightforward, but let's briefly show you bases. And when you look at let's do a strong base, okay? We'll reset this. The pH should be high in terms of, whoops, let's do a strong base. And when you stick this pH indicator in here, it's gonna have a pH of 12. Now notice you don't necessarily, the equation slightly changes, right? So when you're looking through this, this is talking about your base after it's actually mixed with water. So you're basically going to be copying this, and it completely dissociates to form your hydroxide ions. So you're going to have a very, very high pH. When you look at the solvent and the graph, it's basically the exact opposite of the acid idea, in the sense that all of your base had reacted, you're left with a positive charge, and you actually formed your hydroxide ion. Okay. Weak base, same thing, as we were talking about earlier with a weak acid. It's not going to completely react with water. You're going to form some hydroxide, but it's a pretty weak base. So in terms of the conductivity, let's take a look here. Yeah, it's very conductive. I shouldn't say very, because when you compare it to a strong base, you still have these charges. So understanding that should be pretty self-explanatory on what we're looking at. And yeah, in terms of the custom solution, let's talk about this. So this is talking about the pH meter. So this one you actually would have to go to, yeah, setting a custom solution. This is what you're going to be playing around with. So when it's saying set the strength to a strong acid, adjust the concentration and according to pH. So we're going to set the concentration to 0.1, and we need to set it to strong, and that this is what you're going to be recording. So in terms of that, your pH meter, basically what is it reading? pH of 3. So that's really one thing that you're going to be looking at on this one. So other than that, I think the rest is going to be pretty simple. I'm going to move this actually real quick. And I want to pull up one more FET just so we get the idea across. Just to kind of show you another idea here of what acid and bases could be measured with. Where you have varying solutions. So, and there's some interesting ones here. pH. Yeah, so the pH scale, let's look at this one. This is not going to be what you guys are completing, but I just wanted to show you this while I still had you guys here. So let me look at the micro, okay? We're looking at the H3O plus to the OH ratio, so the hydronium to the hydroxide ratio. And if I looked at it, I have equal hydronium and hydroxide ratios. Now, if I kind of adjusted it down here, if I look through this, and let's change the pH. Let's switch something up. If I looked at something that was really acidic, think of something, it's kind of gross, but if you think of like vomit, man, pH in your stomach is really, really acidic. And look at all these hydronium ions. I don't see any hydroxide. And you check the pH, that could definitely, it's going to be acidic for sure, right? You look at something like hand soap. Hand soap is going to have a lot of those hydroxide ions, so it's really, really basic. And you get to things like drain cleaner, really, really basic. Look at all those hydroxide ions. So you can also look at the logarithmic scale in terms of this, your concentration. You have a really low concentration of your H3O plus to your OH minus. So both of these are basically explaining the same thing. This one is a little more, I don't want to say, it's not more simplistic because you're looking at all different variables, but this one is just basically, it's the same thing. It's just showing you that you can actually dilute it by adding water. Because again, if you're adding more water, you're actually going to be changing the pH slightly. But anyway, a couple of helpful simulations on what pH is and how we measure it.